physics class. It's Mr. Duffy. Welcome to our lesson today on free body diagrams. A free body diagram takes into extension like how we represent forces. So we already kind of talked about in our last lesson what a force is. It's again a push or pull. It can cause a change in motion. It doesn't necessarily have to, but it can cause a change in motion. It's represented by the unit of a Newton, and it's a vector quantity, so that means it has magnitude and direction. So since it's a vector quantity, we can kind of like set up a diagrams for it, pictures, to represent where the forces are pointing, since they can point in different directions. So let's take a look at that. So force has magnitude and direction. That's what makes it a vector. But we use force diagrams, or sometimes they're called again free body diagrams, to help visualize how forces act upon an object. So again, if we're looking at a car, maybe it's running into a wall for some reason, um, we can draw the forces acting on the objects, the wall or the car, to kind of analyze what's going to happen with the object's motion. So obviously, if a car runs into a wall, it's going to come to a stop. Um, but we could look at the forces involved. So if we wanted to know again just the force on the car, because maybe that would be more what's going to be relevant to if the person inside survives, we can kind of see the gravitational force and then the normal force, the ground pushing back up, but then we would have the force back on the wall, and so we'd want to know how that one is going to interact, um, how it's going to impact like in the front of the car maybe. Okay, so free body diagrams again are tools for looking at these different forces. So the purpose is to reduce the complexity of the situation so that we can analyze them a little bit easier. The diagram serves as a nice starting point, which is again when we do a lot of our physics problems, we want to have a nice starting point to kind of like work from, and so that's what the free body diagram represents. You can imagine the scenario here. We have this jet airplane, and there are four forces acting on this jet airplane as it kind of flies through the air. We don't know exactly what this object is doing right now, but we know that there would be four forces. And so, if you were to label the four forces acting upon the jet airplane, you probably would come up with something that looks like this. We have lift from the wings, the weight of the airplane being pulled down, thrust from the engine, and air resistance or drag pulling back to the left. And that's basically what a free body diagram kind of is, except for um, we wouldn't want to draw the whole airplane every single time and like a picture, and we're not all artists and stuff. So free body diagrams normally just like, this is a good diagram, but picture, but a diagram is more often in physics drawn like something like this. It kind of removes the object and turns the object into a dot or a box. And so we really just want to know about the forces. That's the physics behind free the forces. So that allows us to analyze them. We don't care necessarily about how great a draw artist we are, when we're drawing the airplane. So that's a free body diagram. Now, let's talk about some of the individual forces that go into free body diagrams next, before we look at, again, some examples of free body diagrams. So some specific forces. Friction is a great example of a force. Friction is always going to oppose the motion of the object. So if the object's moving to the right, you're going to have friction to the left. A book sliding across the desk, and the book is moving to the right, but friction would be to the left. Sometimes we just denote it FF. So force of friction. Basically, friction comes from the two surfaces rubbing together. They have microscopic imperfections there that cause the objects to kind of rub against one another. And that, again, causes a push or a pull, which is a force. Air resistance is a specific type of friction. Normally, we don't just say force of friction, we would say the force of air. Um, it's denoted F sub air there. And again, it's just air resistance is a type of frictional force. Next one we have is tension. Force tension, or normally it's represented with capital F, force T, FT, force tension. And basically that's when we have strings pushing, or ropes, strings like pulling on an object. They cause a tension in the strings, and kind of, again, pushes or pulls the object. So somebody sitting maybe on a swing, you have tension in the ropes that are kind of like holding it up. A good example of force tension. Gravity, force gravity, is always going to pull down. Sorry, that's a large F there. The force of gravity is always going to pull down, and that always points toward the center of the Earth with an acceleration of negative 9.81. Now, with that being said, force gravity is not always, again, it's always a force, but it's not always something that we write it as force gravity. Force gravity causes what we call a weight. We'll learn about that a little bit later in this chapter, but so sometimes you might see it as written as FW because the gravitational force causes a force that we would call weight. And so those are two ways to denote gravity, but it always is pulling down towards the center of the Earth. Normal force is normally, again, normally uh, counteracting gravity. Um, it's kind of one of the forces we might not be familiar with. That we, it's there, but we might not have heard of it before. It's a supportive force, and it's basically creating a stable object. So if a book is resting on a desk, then you have the surface of the book again, gravity's kind of pulling it down, the weight of the object, and then you have an upward force on the book by the desk, and we would call that the normal force. So it supports the weight of the book. Um, there are occasions where the normal force might be at an angle. Again, depends if it's like the person's leaning up against a wall or maybe the person's on a ramp or something like that. You might have a angled normal force, but again, it's still always just a supportive force. It's always again pulling at an angle or sorry, supporting the object. If the object is being supported, if it's like sitting on something. So normal force. Force applied is a force that is applied to an object, as the name kind of sounds. So again, maybe like again, a person's pushing an object or something like that. This would be a little bit different than a tension force because again, a tension force would be somebody like maybe is pulling with a rope or a string. So we would say force tension instead of force applied. But again, the force applied is basically just somebody pushing or pulling an object, and FAPP would be the way we denote it. So a free body diagram again is here to represent the forces acting upon an object. And so here I have a person pulling a sled. So we have a sled across the ice, and we want to draw the free body diagram for the sled. The magnitudes on the forces on the sled are 60 newtons by the string, 130 newtons by the earth, and 90 newtons by the ground. So this, we would just try and keep our force tension here. Try and keep our the length of the arrow is like our magnitude, and so we've got 60 newtons from the string. That's a tension force. We've got a gravitational force pulling down of 130 newtons, so that would be straight down 130. And we could say F gravity or the weight of the object, the weight of the sled, and then we would have 90 newtons pulling back up. 90 newtons is a supportive upward force by the ground, and so that would be our force normal. Okay, and so that would be a free body diagram of the sled. Again, it's just a diagram showing you the forces. We could analyze that later, and that, again, for another lesson. Finally, we've got a physics book at rest on a desk. We have gravitational force pulling it down, so box represents my book. I have a gravitational force pulling it down, force gravity, or the weight of the object, FW. And I have a supportive force from the desk, that'd be force normal. And it says they're equal in magnitude to the gravitational force. So I'm going to just try and make sure that I just kind of make the arrow about the same length here as I made the arrow here. And so the weight down is kind of like, again, equal in magnitude to the normal force back up. No numbers given to me in this problem, so again, I don't have to label any of that, but again, that's what the forces would look like. So hopefully after watching this video, you understand a little bit more of some different types of forces that we have, and then how to represent them using a free body diagram. So thank you for watching.